Okay, let's unpack this truly massive, really ancient topic. When we talk about climate change today, the conversation is usually centered on decades, maybe a century, and primarily human activities, our emissions, our
All
impact.
right.
But what if I told you that the deepest, most powerful driver of climate cycles operates on scales of, hundreds of thousands of years? And it's driven not by industry, but by the very gravitational dance of our planet with the sun and the colossal giants of our outer solar system.
That is exactly the right perspective we need to adopt for this deep dive. We are deliberately stepping back from anthropogenic warming.
Not to say it's not important, of
Oh,
course.
absolutely not. But we're framing it within this vast, almost indifferent context of geological time. Today, we're analyzing the ultimate celestial clockwork of the Earth, the Milankovitch cycles.
So just to define this really clearly for you, what we're talking about here are, well, they're the collective effects of these three main changes in how the Earth moves.
Exactly. You've got its path around the
And
sun,
its orbital path, right?
its tilt, and its wobble. And all three of these things, they change how much solar energy we receive.
And that, over millennia, is what really drives the climate. These aren't just, minor seasonal shifts. These are the slow, powerful rhythms that govern the waxing and waning of continent-sized ice sheets.
And determine whether we're in a glacial age or a warm interglacial period like we are now. And, this isn't just a vague theory anymore. The definitive quantitative analysis that really cemented this concept came from one man, Milankovitch.
He was a Serbian geophysicist,
Yeah.
astronomer, right, back in the 1920s.
That's him. He took this earlier, sort of more qualitative idea from a 19th century scientist, James Kroll, and he gave it this rigorous mathematical framework. He figured out that these shifts were predictable and measurable.
So he turned a geological idea into predictive climate science.
Precisely. He didn't just suggest the Earth moves, he quantified the climate consequence of that movement. His work established mathematically that these cyclical orbital variations result in predictable changes in the distribution of solar radiation at the Earth's surface.
A process that scientists call, solar forcing.
Solar forcing or radiative forcing,
Yeah.
yeah, it's the engine driving the cycles. And so our mission today is to unpack the mechanics of the three components that make up this forcing, and then delve into the sometimes profound and genuinely puzzling impacts they leave documented in Earth's history.
And crucially, Milankovitch didn't just model the average solar radiation hitting the globe. That would be, I guess, too simple. He focused specifically on how these energy changes happened at a very particular place on Earth.
65 degrees north latitude.
Okay, why there? Why 65 degrees north?
That geographic emphasis is really the tactical core of his entire theory, because that latitude is where you find the largest amount of continental land masses in the northern hemisphere. It's where the giant kilometer-thick ice sheets have to initially form.
So why does the ratio of land to sea matter so much for setting off an ice age?
It all comes down to something called thermal inertia. Land masses change their surface temperature much, much faster than oceans do.
Oceans are like a giant thermal battery.
A perfect analogy. They have this enormous deep volume of water, and with constant mixing, they have a huge thermal inertia. They take thousands of years to warm up or cool down significantly, but at 65 degrees north, if that land is exposed to less intense summer sunlight, it cools rapidly.
And if the snow from the winter doesn't completely melt?
That's the gateway. That's the starting point for massive permanent ice sheet formation. Snow persistence is the key to a full glacial period, and 65 degrees north is the threshold.
So Milankovitch essentially found the Achilles heel of the Earth's climate system, a spot sensitive enough to translate astronomical forces into geological consequences.
Now that we've established the why, let's get into the mechanics of the how. It's hard enough to model the gravitational dance of just the sun and Earth, but when you factor in the massive tugs from Jupiter and Saturn,
The big guys.
you end up with these three complex, slow, cyclical variations in Earth's relationship with the sun. We need to break down each one.
Absolutely. So think of these as three different ways the Earth is subtly jostled as it orbits the sun, each with its own rhythm, its own cycle length, and its own unique climatic consequence.
First up is orbital eccentricity.
Okay, eccentricity. If you're like me, you probably think of Earth's orbit as a perfect circle, but it's actually an ellipse. And eccentricity just measures how much that ellipse departs from being a circle.
That's right. And the shape literally breathes over time. It can get very, very close to being perfectly circular with an eccentricity near zero. But looking back at the records, the most elliptical our orbit has been was about 0.0679.
Which is still only mildly elliptical, right? It's not like a comet's orbit.
Not at all. But that mild stretch is incredibly important, and the cycle times here are massive. This is where we start talking about real deep time.
So what's the rhythm?
The dominant fundamental beat is immense. 405,000 years. That's the pace dictated by the gravitational resonances in the solar system.
405,000 years. That's the huge, slow-breathing rhythm. But we also hear a lot about a 100,000-year cycle when discussing ice ages. Where does that one come from?
That comes from the interplay of two other significant shorter components. One is about 95,000 years, the other about 124,000. These two components, they sort of reinforce and diminish each other.
And they combine to create what we call the crucial 100,000-year cycle.
Exactly, and that's the primary pattern we see governing the ice ages of the last million years, which, and this is a huge point of confusion we will absolutely come back to later, is a massive puzzle.
So the 405K is the foundation, but the 100K period is the one that's been driving recent glacial cycles. Where are we on that spectrum today?
Right now, Earth's orbit is actually quite circular. The current eccentricity is only 0.0167, and it's decreasing. So our orbit is getting even more circular.
And what's doing the heavy lifting here? Changing the shape. It's not just the sun.
No, it's entirely external forces. It's primarily the massive gravitational influence of the gas giants Jupiter and Saturn. They're the ones constantly tugging on the Earth-Sun system, subtly stretching and compressing our path.
Okay, here's a critical piece of physics that I think often gets mixed up. If the orbit stretches into an ellipse, does the year get longer? Does our average distance change?
That is a fantastic, deep question, and the answer is no. While the shape of the orbit changes, the semi-major axis, which is basically the average distance from the sun and therefore the length of the year, they remain fundamentally unchanged by these variations in eccentricity.
Let me try an analogy. So if you imagine our orbit is like a rubber band stretched into a perfect circle, and then you just squish it slightly into an oval, the total amount of rubber band doesn't change. So the time it takes to travel around it doesn't change either.
That's a perfect visualization. The orbital period doesn't alter. What changes is the difference between your closest point and your furthest point, and as we'll see, the speed at which you travel between them.
Okay, moving on to the second movement. The axial tilt, or obliquity. This is the angle of the Earth's axis relative to its orbital plane, and it's the reason we have seasons.
Exactly. The axial tilt is just the planet leaning over as it spins. This tilt varies gently between a minimum of 22.1 degrees and a maximum of 24.5 degrees.
That's only about 2.5 degrees of swing. It doesn't sound like much.
It isn't a huge swing, but it is incredibly potent climatically, and it happens over a relatively swift cycle of about 41,000 years.
And where are we on that clock right now?
Our current tilt is 23.44 fixed degrees, so almost exactly halfway between the extremes. And we can track its history with amazing precision. The tilt last reached its maximum in 8,700 BCE.
Which correlates pretty well with the end of the last ice age and the start of the Holocene, the warm period we're in now.
An incredible correlation. And since then, the tilt has been decreasing. It's scheduled to reach its minimum around 11,800 CE.
So what does a greater tilt actually do to the climate? I think people often assume a greater tilt just means more global warming.
That's the key misconception. The total amount of energy the Earth gets globally doesn't change based on tilt. A greater tilt just acts as a season amplifier.
Hotter summers, colder winters, more extreme seasons.
Absolutely. But here's the specific Milankovitch insight, linking back to 65 degrees north. Increased tilt dramatically increases the total annual solar radiation received at those high latitudes. If the Earth is tipped over more, the poles get a more direct blast of sunlight for longer.
So it's stealing energy from the equator and dumping it at the poles year after year.
And that leads directly to the implication of our current trend. Because our axial tilt is currently decreasing, that trend by itself promotes milder seasons, specifically less intense summer heating at high latitudes.
Which means less summer melt.
And less summer melt means the snow and ice from the previous winter can survive.
So the trigger for an ice age isn't a super cold winter. It's a summer that is just barely cool enough to let the snow survive.
Precisely. That persistence of snow cover at that critical latitude, decade after decade, allows the ice sheet to grow. The 41,000-year cycle of obliquity is the great accelerator of ice melt and ice sheet growth.
Our third movement is maybe the most dizzying, because it involves two distinct physical components that interact to create a third, climatically relevant cycle: precession. Let's start with axial precession.
Axial precession is the classic wobble. If you think of the Earth like a massive spinning top, its axis of rotation slowly traces a circle in space relative to the fixed stars.
Which is why Polaris is our North Star now, but in a few thousand years it won't be.
Right, the axis will be pointing somewhere else. This full wobble cycle takes about 25,700 years, and it's caused by the gravitational tug of the sun and the moon on Earth's equatorial bulge.
Okay, so the axis is wobbling, but there's also something called apsidal precession. What's that?
Apsidal precession is the rotation of the elliptical orbit itself in space. Imagine the entire orbital ellipse physically rotating, very slowly, like a giant dial. This cycle is much longer, about 112,000 years, and it's driven primarily by Jupiter and Saturn.
So the axis is moving, and the track the planet is running on is also slowly rotating. That feels incredibly complex.
The mechanics are complex, but the climate outcome is simplified. The key is that these two precessions combine to vary the position in the year that Earth reaches perihelion, its closest approach to the sun.
And that combined cycle is about 21,000 years.
It's about 21,000 years at present, yeah. And that cycle determines which hemisphere gets its summer boosted by being closest to the sun.
Let's talk about the current situation, because it explains a lot about our climate today.
Okay, so right now we reach perihelion, our closest, fastest approach to the sun, around January 3rd. That means perihelion happens during the southern hemisphere summer.
Which creates a recipe for extremes in the southern hemisphere.
Absolutely. For the southern hemisphere, the effect of the axial tilt being tilted toward the sun and the proximity effect being closest to the sun are perfectly additive. They combine. This results in far more extreme seasonal variation.
Hotter summers, colder winters down south.
Right. Meanwhile, the northern hemisphere gets a bit of a break right now. For us in the north, the effects are opposite. We are tilted toward the sun when the Earth is furthest away at aphelion around July 4th.
So the two effects work against each other, giving us milder seasons.
Exactly. But the clock keeps ticking. In about 13,000 years, the alignment will have reversed. The North Pole will be tilted toward the sun at perihelion, and then the northern hemisphere will be the one with the more extreme seasons.
Okay, that was a powerful breakdown of the physics. Now let's translate that into the real sensory consequence. How these movements actually change the experience of seasons and climate.
Right. How do we convert this abstract geometry of wobble, tilt, and stretch into practical, usable solar energy insulation, which is what actually drives the climate system?
Let's revisit eccentricity. We established our current orbit is nearly circular, with an eccentricity of just 0.0167. How much does that small departure from a circle affect incoming energy right now?
Because the orbit is so close to circular, the variation in incoming solar radiation between our closest point and our furthest point is only about 6.8%. It's a relatively small variation.
So the axial tilt is much more important for our seasons today.
Dominantly so. But if we went back to a time when eccentricity was at its maximum, that swing would be way more intense.
Okay, more.
It would jump to about 23%. That's a massive difference, almost 4 times what we have now. It fundamentally alters the seasonal contrast, especially for the hemisphere having its summer at perihelion.
Now for the part that I find really surprising, eccentricity's role in the length of the seasons. This is thanks to Kepler's second law.
This is one of the most elegant connections. Kepler's second law basically says a planet moves faster when it's closer to the sun and slower when it's farther away.
And since we're closest in January, we're rushing through the northern hemisphere's winter and then dragging our heels during its summer.
Exactly. And we can actually quantify this. For the northern hemisphere, summer is currently 4.66 days longer than winter.
Nearly 5 days, just based on how fast we're swinging around the sun.
And that's climatically critical, especially for that 65 degrees north threshold. A longer, cooler summer, which we currently have in the north, provides less overall heating. When you stack that slight reduction in heat over thousands of years, those extra few days make it easier for snow and ice to persist.
It's the cumulative multi-millennial effect that really matters. And you said our orbit is becoming more circular.
It is, which means the difference in speed will lessen, and the lengths of the seasons in the immediate future will become more similar. That 4.66-day disparity will shrink.
So let's just underline obliquity's impact one last time, because it was the central trigger Milankovitch identified.
The whole theory pivots on this idea. The amount of summer insolation at high northern latitudes is the absolute key to melting the massive ice sheets. The winter temperature is almost secondary. You can have a brutally cold winter, but if the summer is intensely warm because of a high axial tilt, all that snow just melts away. No ice age.
But with the tilt decreasing as it is now.
We get less summer insolation at those high latitudes, and that means the previous winter's snow and ice can persist. A few degrees of tilt reduction at the right latitude is enough to tip the system toward glaciation. It's a razor's edge.
Okay, now let's shift gears. We've done the physics, now for the messy geological evidence. The data confirms these cycles control ice ages, but it also introduces these profound problems or discrepancies.
Right, these are the mysteries that scientists are still actively working to solve. This is where the simple astronomical model meets the complex reality of Earth.
I find this part the most fascinating. But before we get to the puzzles, where does this rock-solid climate history actually come from?
Our most reliable, high-resolution records come from Antarctic ice cores. You drill deep into the ice, pulling up columns that go back hundreds of thousands of years.
And they have little trapped air bubbles.
Trapped air bubbles that preserve the atmosphere from that time. But even more critically, scientists analyze the ratios of different oxygen isotopes, oxygen-18 versus oxygen-16, in the ice itself.
And those ratios are a proxy for temperature.
Exactly. They indicate past global ice volume and temperature. And the analysis of this data definitively concluded that the climatic response was driven by northern hemisphere insolation, just as Milankovitch hypothesized.
And it's not just ice, right? We have other records.
We do. Deep ocean cores and cores drilled into ancient rock formations provide the long-term validation going back millions of years. Cores from Arizona, dating back 215 million years, show climate patterns perfectly synchronized with Earth's long-term eccentricity variation.
So the foundation of the theory that orbital cycles affect climate is absolutely sound. But as you said, the data is almost too clear, which leads to the paradoxes.
Let's start with the biggest one. The 100,000-year issue, or the 100K problem.
Okay. Milankovitch predicted that the obliquity cycle, the 41,000-year rhythm, should be the dominant driver of ice ages because it's the most powerful lever on high-latitude insolation. So what did he get wrong?
He got the physics right, but he underestimated the complexity of the climate system's internal response. His model deduced a 41,000-year period for major ice ages, but the reality, confirmed by all the geological data for the last million years, is that the major ice age cycles have primarily occurred on a 100,000-year cycle.
Wait, hold on. That 100,000-year rhythm is tied to the relatively weak eccentricity cycle. So the strong 41,000-year signal from the tilt should dominate, but the climate response is dominated by the much weaker eccentricity period.
That is the central paradox. Why does the weak signal win? It suggests that eccentricity isn't just a driver of climate, but maybe more of an orbital switch or a gatekeeper that controls when the powerful internal climate feedbacks can activate.
So it must require some massive nonlinear interactions to amplify that tiny astronomical nudge. What are the leading explanations?
The first is classic climate system feedbacks. The idea that small orbital changes trigger massive nonlinear responses in CO2 levels or in the growth and decay dynamics of the ice sheets themselves.
And then there's a more elegant theory.
The more specific one called stochastic resonance. This posits that the climate system isn't just passively receiving the signals, it has its own internal low-frequency oscillations. And when the weak 100,000-year orbital forcing hits it at just the right frequency, it manages to lock onto and amplify that beat.
It turns a whisper into a roar.
Precisely. Another concrete idea is the sea ice hypothesis from researchers like Zhongyun Lee at Brown University. This theory suggests the southern hemisphere plays an unexpectedly strong role.
Why does the southern hemisphere sea ice matter so much when Milankovitch said 65 north was the key?
Well, Lee argues that precession only really matters when eccentricity is large. And crucially, the southern hemisphere's massive ability to grow and hold reflective sea ice provides a powerful albedo feedback.
Albedo, the reflectivity of the surface.
Right. So even when the South Pole gets blasted with extra sunlight, the massive reflective blanket of sea ice just bounces a huge amount of that energy back into space. This difference in energy reflection sets the stronger 100,000-year pace because the whole system is gated by when eccentricity allows those ice dynamics to change.
That's complex, but it's elegant. Then there's the mid-Pleistocene transition. We know the 100K problem is geologically speaking, recent.
It is. From about 1 to 3 million years ago, the climate cycles actually did match the expected 41,000-year obliquity cycle. The system behaved exactly as Milankovitch predicted.
And then, around a million years ago, it threw a switch and shifted to the 100,000-year cycle. What happened?
That's a major area of research. Recent simulations have had some success. They show the transition can be explained by two key non-orbital factors. First, a long-term decline in atmospheric CO2, which cooled the baseline climate, and second, the glacial removal of regolith.
Regolith. That's the loose soil and rock on top of the bedrock.
It is. For millions of years, the ice sheets had been scraping away at the continents. By about a million years ago, they had basically scrubbed the ground clean of most of this loose material.
And why does that matter for the climate cycle?
Regolith acts as insulation and a lubricant. Without it, the ice sheets are sitting on bare, resistant bedrock. They became much more stable and much harder to melt. This increased inertia meant the climate system became locked into the longer, slower 100,000-year cycle.
Amazing. The consequences of past cycles fed back and changed the pacing of future cycles.
And finally, there's the causality problem. This is a big chronological headache. The evidence shows the last major interglacial period, the last big warming, began 130,000 years ago.
Okay, and the problem is?
That is 10,000 years before the peak solar forcing predicted by the hypothesis. The climate warmed up significantly before the maximum summer sunlight actually hit the Earth. The effect seems to precede its cause.
So the initial warming was accelerated by something else. The orbital cycle was the trigger, but internal feedbacks took over and floored the accelerator.
Exactly. It implies that the initial smaller change was enough to start melting the toe of the ice sheets, which then kicked off a massive feedback loop like exposing darker ground or releasing CO2 that took over and ran away with the process.
This journey through the deep past and its puzzles is astounding. Let's bring it back to the present and look at the future. Since these cycles are predictable, we should be able to forecast the next few ice ages, right now?
In theory, yes. The astronomical models are incredibly accurate. But, and this is the massive caveat, we are no longer living in a purely natural system. We have to account for the huge increase in greenhouse gases from human activity.
Of course. But let's push that aside for a moment. What did the early models predict based only on the natural cycles?
An influential 1980 model predicted that a long-term cooling trend that actually began about 6,000 years ago would continue for the next 23,000 years.
So we should be slowly heading into the next ice age.
Based strictly on that natural cycling, yes. However, more recent refined work paints a much more comforting natural picture. The key is that Earth orbit is going to become less eccentric for the next 100,000 years.
So the gatekeeper, eccentricity, is weakening.
Which means its impact will lessen, and the insulation changes will be dominated by the decreasing obliquity, the continued mildening of seasons. But here is the critical calculation. The reduction in solar energy at 65 degrees north will simply not decline enough to permit a new glacial period in the next 50,000 years.
50,000 years. That is an enormous window of natural stability. It means that even if humanity vanished tomorrow, we were naturally set up for an exceptionally long interglacial.
It's a crucial finding. The long-term background is stable. The short-term anthropogenic change is the immediate issue. The beauty of these cycles, though, is that they're universal. Any planet or large moon will experience them.
And the clearest non-Earth example is Mars.
Absolutely. Mars is a great example because it makes us appreciate our own stability.
Yeah.
It has no large moon to stabilize its axis.
Which leads to much more dramatic changes in its tilt.
Wildly dramatic changes. Earth's tilt varies by a mere 2.5 degrees. Mars's obliquity has varied from a low of 10 degrees up to a staggering 70 degrees.
70 degrees. That's planetary chaos. The poles must sometimes point almost directly at the sun.
It certainly does, and it explains these massive past climate changes, like the total disappearance and reappearance of its polar caps. When the poles tilt that far over, the entire climate system goes haywire.
That really puts Earth's relative stability into sharp perspective, all thanks to our moon. Do these cycles extend even further out?
They apply universally. We see them on the moons of the gas giants. Saturn's enormous moon, Titan, has a precession cycle of about 60,000 years. And scientists think this cycle might be responsible for shifting the location of its liquid methane lakes over time.
That's a mind-boggling thought. Orbital mechanics causing lakes to migrate across an icy world. And what about exoplanets and the search for life?
Well, when scientists model exoplanets, they often have to account for these extreme axial tilts, just like Mars. That could pose a difficulty for specialized land-based life.
But does it make a planet uninhabitable?
Not necessarily. The consensus from modeling is that most such planets would still allow for the development of both simple and complex life, provided the planet has a stable atmosphere. It suggests life is surprisingly resilient to this kind of orbital chaos.
This has been a true deep dive into cosmic rhythms. We started with the three motions, eccentricity, obliquity, and precession, and learned how their slow, predictable effect governs the planet's massive ice ages.
We also saw that this ancient process is far from perfectly understood. The 100,000-year puzzle required us to invoke these complex internal climate feedbacks to explain why a weak astronomical signal yields such a powerful response.
The orbital rhythm is the clock, but the Earth's internal systems set the volume.
A perfect way to put it. And as we close, that reference to exoplanets brings us back to Earth's most fundamental advantage.
Our moon.
The stabilizer. Exactly. It acts as our essential orbital stabilizer, preventing that Martian-level chaos and keeping our axial tilt within that comfortable, narrow range. We take it for granted, but it's the reason our climate has been so relatively stable.
It's the luck of having a massive satellite close by.
Indeed. But here is the final provocative thought. While the moon protects us now, its stabilizing effect isn't permanent. Due to tidal forces, the moon is slowly receding from Earth about 3.8 centimeters per year.
A tiny amount.
Tiny now, but over deep time it adds up. In the far, far future, we're talking 1.5 to 4.5 billion years from now, the moon will have receded far enough that its gravitational influence lessens significantly. And at that point, Earth's obliquity could escape its current stable range.
So we could end up like Mars.
It's possible. The poles could eventually point almost directly at the sun, experiencing the 70-degree tilts that Mars endures now. Imagine a scenario where the poles, instead of the equator, receive maximum continuous sunlight. That would create a climate state of unimaginable extremes, far beyond anything we've discussed today. It really makes you consider just how precious and how fragile Earth's current orbital stability truly is.